In this video, we're going to introduce and describe time complexity, which is a fancy way of saying we're going to measure how long it takes programs to run. We're also going to talk about big O notation, which is a shorthand for representing how long it takes programs to run, and allows us to work with different time complexity classes. Time complexity is just a fancy way of saying the running time for programs. So in this section, we're going to talk about how long it takes programs to run, and we call this by its fancy name, time complexity. We're only going to consider computable functions. That means functions that are decidable by a Turing machine. And in particular, remember that decidable functions always terminate, always halt. And that makes sense because we can't really consider the time it takes for programs to run when they do not halt. So we'll only look at decidable functions, and we'll only consider deterministic machines. We have talked in other videos about non-deterministic machines, and they have this wonderful ability to guess the right thing or try all possibilities. But this is a questionable operation and something that you don't see in real machines. So we're not going to consider non-deterministic machines, at least in the beginning here. Later on we will talk about other complexity classes that involve non-determinism. But for now, let's just restrict our attention to machines that are similar to real machines, and in particular to deterministic machines. So the first thing we want to do is remember that each time you run a program, you run it on some particular input. And so we will want to measure the time it takes the program to run on a given input, W. We'll be looking at Turing machines, since that's the model of our computation. And the running time of a Turing machine is just the number of transitions it takes. So we just start our Turing machine and count how many transitions it takes before it halts, and that will be the running time. And the next thing we want to do is not look at just one particular input, but we want to consider all inputs of a particular size. So in a Turing machine, we measure the size of an input by the number of cells it takes to represent that input string on the tape, and that's easy enough to just count. We will then ask about all inputs of a particular size, and the program or the Turing machine is going to take a different amount of time to run on some inputs than other inputs. Some inputs of a given size may be fairly easy to do, and other inputs of the same size may require a lot more computation. So we're concerned about the maximum running time our Turing machines take. And in particular, we want a function of the input size. So our goal in determining how long a Turing machine takes to run is to find and write or create a function, and that function is a function of n, the size of the input. And for every value of n, it describes the maximum time a Turing machine might take to run on an input of that size n. So we'll look for functions that describe the running time in that way. So given a particular Turing machine, or given an algorithm described in your favorite programming language, let's assume that you can come up with a function to describe exactly what the maximum running time might be for all inputs of a given size. Generally, that function is going to be very complex and very ugly. Here I've just shown an arbitrary function that I just made up, but it gives you the idea that the function can have a number of different terms, and these terms can have all kinds of things going on in them. And so we find the running time for inputs of size n, the maximum running time, might be some complex, ugly function. And we like to simplify things. And to do that, we really care about the running time for large inputs. So we care about large values of n, and we look at that function and we say, well, what's this function do when n gets really large? And the answer is many of the terms become irrelevant, and one term in this particular function, it's this 17n cubed function term, the 17n cubed term begins to dominate at large values of n. So what we'll do is we'll take our functions and we'll ask about the asymptotic upper bound. Okay? The asymptotic upper bound. In other words, we're asking what these things do when n gets very big, and what sort of their asymptotic behavior is. And we'll describe this with something that we call big O notation. This is the order of the function, or we use the terms big O. And so in our particular case, the term that dominates this was the n cubed term. So we'll write a big O in parentheses to say that this function is n cubed. So this O here is not really a function directly. This is more notation than anything. But what we're doing is we're trying to express the idea that this function, my complex 17n cubed plus 5n squared function, has asymptotic behavior of n cubed. So here I've tried to draw a graph of what this function might look like. Okay, and so the idea is that the function does all kinds of crazy stuff for small n. But as n gets larger and larger, that is, as we try to run this algorithm or this Turing machine on inputs of greater and greater size, the n cubed term begins to dominate, and eventually this thing sort of approaches, or asymptotically, the curve n cubed. And so this term n cubed is the one that we really care about. And also with our big O notation, we're going to ignore constant factors. In my original function, I had a factor of 17 out in front of the n cubed term, and we don't really care whether it's 17 or 3 or 49. What we really care about is the fact that this function is behaving cubically as a function of its input. So we care about the n cubed, and we don't care about the constant factor like 17. So we want to ignore that as well and just go with the main n cubed term. So let's now start with a definition of time complexity. Let's let M be any deterministic Turing machine that always halts, and we'll let n be the size of an input. Then we can define the time complexity of M as the running time of M, and we define the time complexity as a function f, which is just the maximum number of steps that M takes on any input of size n. Now, we're talking about Turing machines, and for a Turing machine, the input size is just the number of cells on the tape. So the size of the input generally means the length of an input. When we're talking about other algorithms that are expressed in other ways besides as Turing machines, then we're generally talking about the length of the input to those algorithms. However, for many algorithms, we might really care more about not just the length of the encoding of the input, but we might care about something that's more closely related to the problem. For example, if we have a algorithm that does some sort of a graph computation, for example, looking for paths or checking for connectivity or something like that, we might be more interested in the number of nodes in the graph, or maybe perhaps the number of edges in the graph, rather than just the length of some encoding of the problem. Likewise, if we are looking at a program that, for example, parses an input string relative to some context-free grammar, we might be more interested in the number of rules in the context-free grammar, or something like that. And in these cases, it might be easier to find a function that is in terms of the nodes in the graph, or the rules in the context-free grammar, or some other aspect of the problem. But the length of the input is generally closely correlated with those things anyway. For example, in a graph problem, you might be searching for a path through the graph, and you have to specify the graph. You have to specify and represent the graph as an input to that algorithm. And so you have a bunch of nodes and edges and so on, and you have to somehow represent those using symbols, and that input then is fed into either a Turing machine or some other expression of the algorithm. Well, there's a close correspondence between the number of nodes in the graph and the size of the representation of that graph. If you double the number of nodes in the graph, then presumably the representation of the graph is going to double as well. Now, it may not be exactly the case. You also have the edges to consider, and if you double the number of nodes in a graph, you might quadruple the number. Quadruple the number of the edges in the graph. But generally, there's some sort of a polynomial relationship between the size of the problem expressed in whatever makes sense for the problem and the size of the input. So we'll just look at the size of the input or the length of the input as our n, which is the parameter to our time complexity function f. Many of our functions that express running time will be of the form of polynomials, such as the one I gave before. And in order to figure out the order of this polynomial, the rules are pretty simple. We just take the highest order term. Okay? In this case, we have a linear term, a squared term, and a cubed term. So we just look at the highest order term, which in this case is n cubed, or 17n cubed, and we ignore the coefficient. So that gives us n cubed. So we write that information this way. F of n is order n cubed. Now there are other ways we might, for different functions, not this function, but some other function f, we might say it's n to the fourth or n squared or something. We also want to say that this particular function f is order n to the fourth and n to the fifth and other polynomials as well, because those are greater than n cubed. This function is not order n squared, but it is order n cubed and n to the fourth and n to the fifth and n to the sixth and so on. We also have exponential terms here. This function doesn't contain anything like that. N is not used as an exponent, but polynomial orders are all included in exponential orders. So we can properly say that this function f is also order 2 to the n. Next we'll give a precise definition, but before we give the precise definition of order notation, let's summarize it here. So let f be some running time function of some algorithm that we're interested in. Then we say that that function has order, for example, n cubed, if for all n that are greater than some arbitrary value, some big value. In other words, for when n gets large enough, then f behaves like n cubed, at least ignoring constant factors. It behaves or looks like or has the same growth as n cubed, at least as long as you ignore the constant factor in front of the n cubed. Now our more precise definition is here. We say that f of n is order g of n if there exists some c and there exists some n0 such that the function is less than or equal to c times g to the n for all n large enough, that is, all n larger than n0. F is order g of n if g of n multiplied by some constant term grows at least as fast as f for n that are larger than some value n0. Let's look at some typical complexity classes that we see fairly frequently. First of all, n, a simple function with no exponent, is linear. a function that is order n is a linear function. We also see log n log n. Here's n squared, or n to some other power, such as n cubed. We might, in general, say n to the k to mean polynomial time in general. So all of these, up through n to the k, are considered polynomial time. When n enters the exponent, we enter the realm of exponential time algorithms. And so we express exponential algorithms as 2 to the n. And so, corresponding to each of these, we have the order classes. So order n means a linear time algorithm. In other words, an input that's 3 times as long will take 3 times as long to run. N log n is a common complexity class. N squared, n cubed, occasionally n to the 4th. And then we jump to exponential algorithms. So in this slide, I want to show you the different kinds of running times and the different functions that are of interest. So here I'm plotting n and the various different functions, so you can remember what these are. We'll start with the linear, which is just a straight line right here. Log n grows slower than linear, and n log n grows just a little bit faster than linear, so they're kind of close to linear, if you will. And then we have the polynomial functions, n squared, n fourth, and so on, up to n to the k. And these are sort of intermediate in range to the linear types of functions. And then over here we have exponential functions. And I think it's important for you to remember that exponential functions grow much, much faster than polynomial functions. For example, if you have an algorithm that runs in n cubed time, or approximately n cubed, order n cubed time, and another algorithm that runs in 2 to the n time, let's consider an input of size, say, 1,000. Well, the n cubed algorithm runs 1,000 cubed, which is a billion. So on the order of a billion instructions or a billion transitions or whatever. It's a large number, but it's not super huge, and it's still in the realm of computation, even if there's a constant factor out there and it takes 17 billion instructions. That's something that your computers can do. On the other hand, if you look at another algorithm that runs in exponential time for the same size input of 1,000, 2 to the 1,000 is a huge, huge, huge number that is beyond any conceivable computing machine that might ever exist. I mean, you're beyond the area of science fiction when you're talking about a number this big. You will not be able to run something with 2 to the 1,000 steps. Okay, it's just not ever going to be a runnable algorithm. So exponential algorithms and polynomial algorithms are in completely different classes, shall we say. Polynomial algorithms may take a long time, but they're doable. Exponential algorithms are rarely ever usable. Only for very small values of n is an exponential algorithm ever going to be feasible or runnable. Now let me talk a little bit about algorithms that run in order log n. There aren't very many useful algorithms that have this runtime behavior. And you might ask, why isn't that? Well, the answer is that the input has a size of n. And just to read all of the input requires an algorithm of order n. In other words, at least it has to be at least linear in the size of the input. So any algorithm that runs in order log n time doesn't have enough time to read even the input. So it doesn't make sense, really, to have an algorithm. It basically has to ignore its input. So it's in that sense, it's not a very interesting algorithm. Now that we have our order notation, we can talk about all the problems that can be decided in a particular amount of time. Order n is just linear time. There are many, many algorithms, many useful algorithms that are order n, that are linear algorithms. And we can talk about all the problems or the languages that can be decided in linear time and create a separate class of problems. So remember, these are all decidable problems. Okay, we're not talking about Turing recognizable or other sorts of problems. We're talking about algorithms that will halt. So these are all subdivisions of the category of decidable problems. And we can denote with this notation, time n, the set of all languages or the set of all problems that can be decided in linear time. This would include, of course, all regular languages, because a regular language can be decided with a finite state machine, and that finite state machine scans through the input, and for each character the input takes one transition. So the running time is just n, the length of the input. So that is certainly linear time. There are many other problems that can be decided in n² time, and those are in the category time n². And then likewise, there's a large class of problems that can be decided in n³ time. All context-free languages can be decided in n³ time, and many of them can be decided in lesser time, but many can be decided in n³ time. N log n is also a big class. I haven't really put these things in proper order. Really, I should put n log n before n², since all n log n algorithms are n², but there are n² algorithms that are not n log n. N log n is just a little bit more than linear, whereas n² is a larger class. So it should read linear, n log n, n², n³, n to the fourth, and so on. And then above all of those, we have exponential time. So here I say that more specifically, all linear algorithms are in fact n log n as well, but there are some n log n algorithms that are not linear. Likewise, there are n² algorithms that are not n log n, and n³ is a bigger set. These are all proper subsets. N to the k stands for all problems that are polynomial, so whatever the exponent. This is the set of all polynomially solvable problems, all algorithms that run in polynomial time. And then we have the exponential time up here. And there are some algorithms that apparently run only in exponential time, and that cannot be done in polynomial time. I said apparently. I'll get back to that in subsequent videos.